good job, clever job organizing it. That's very important to have some kind of conferences where people of different areas are combined in a listening together, and even supposed to be is not only just the purely scientific talk on the work, but also to give some kind of discussions, opinions, and this kind of information. This is, in my point of view, it is very important. And so I decided to divide my talk into parts. One of them is going to be main body of my talk, whose title is Topological Phenomena in Real Physics, and whose my intention is to speak about my very concrete, specific work about quantum solid state physics of normal metals. But before that, I just let me remind you that our conference has been called Visions 2000. And let me present you 10 minutes of visions. Yes, I would like to combine this kind of before that. After that, I will go to the main scientific body of my talk. Well, how is transparency? That's yesterday, Yuval Neyman spoke about how our science started in ancient Greek. Yes, you see, I read a lot about that, and what I found out, Yuval also mentioned this yesterday, that this famous guy was first, has been taught in Egypt, after that in Babylonians, like that. I read biography of Pythagoras, who also has been taught many years in Egypt, after that taken prisoner by Persians to Babylonia and came back to 58 years old, and he started his activity. So, and what I read also from Plutarchus is following, that when Aristotle published his famous natural philosophy, one of his pupils, important pupil indeed, Alexander the Great, sent letter, very angry letter from Persia, where he was temporarily occupied by making a famous war, that Aristotle is very much guilty that he published knowledge which has been told before in hidden mysteria. At that time, people did not thought, as in our primitive works, that Aristotle invented it, that he exposed it publicly. And after that started real development. So real invention of this Greek people was in fact openness of information. That's and importance of this is obvious. Is only after that our real science started, and they attribute everything what was known before to them, but we cannot find out as if what was told in hidden mystery and so on. It's difficult to recover any real authors beyond that. Yes, that is what. That's okay. I get what I wanted. For me now is ancient Greek as who created science as an openness of information. This is the real point of our science, and this just in my visions. I will say something about that, and so. This is real openness of information, openness of discussion, scientific discussion, of course. That's by the way, in Roman Senate, it was not considered as insult if anyone told very hard work about other one in process, but we should not use that. Anyway, our discussions should be open, and I heard many times from different physicists, for example, that mathematics community is strange community, doesn't make any discussions, any open discussions. So this is importance of this conference is that we are going to start some kind of breakthrough in that direction to make information open. Well, let me remind you a little bit. As a topologist, I spent years working in that area and still are coming back to it. And several times, when I'm coming back to it now, in the main body of my talks. And let me tell you a little bit about history of topology during the last 50 years. The so-called golden period of classical topology has been lasted between, say, during the period of 50s and 60s, as I believe. In this period, a huge number of important ideas has been invented. That's new dimensions in algebra, in analysis and partial differential equations, in geometry, dynamical systems, algebraic geometry, and even number theory has been created in that period. This style of mentality has been used, different combination of abstract categorical arguments combined with concrete geometric intuition and analytical and algebraic calculation. This is what is important, what has been characterized in classical topology of that theory. This combination of all that, that kind of arguments, mentalities, abstract and concrete. And last point is following that all periods, all works, all important works of that period were properly checked, written, published completely, fully published. It is unfortunately the topology of that period is not covered by material in textbooks, in any textbooks. Textbooks covers part of this material written later. Textbooks covering it are written in very abstract terminology and completely impossible to read. Abstract or formal or something obviously written by people who did not create it. And by the way, I asked my students in Maryland, why don't you use for learning topology one of remarkable classical articles like Jean-Pierre Serre-Fenot's work, from which I myself learned instead of using stupid abstract textbooks written much later. It is much better than any kind of textbooks. Or they answered me, it is not translated yet in English. It's really impossible to use it. So more or less, starting from that period, it is not exposed properly in the textbook literature in form which really gives you real mirror of what really was happened in that period. In 70s, period of 70s, I consider as end of this golden period some period of decay. It does not mean that I don't say that no good results have been obtained. But there were, I would like to give you some very good and important results were obtained, some development happened, and so on. But there was crisis of subject. Some of this kind of crisis Misha Gromov mentioned, so maybe I would say number of way constructing manifolds became less than number of ideas in topology, and so it's some kind of subject became too narrow for this collection of ideas. So society dispersed, the community dispersed in different areas of mathematics and mathematical physics and theoretical physics, different branches of mathematics and mathematical and theoretical physics, and so huge part of leading people left this area. And the third point is a following one. Some kind of informational mess has been created, from that period. Good to know that some very important results, which were invented by some outstanding scientists, like, for example, Half-Fermiton theory, classification of topological structures, theory of elliptic structures on manifolds, are not written with full proof until now in any literature. So, and indeed, this is, for me, it is just some kind of thermometer indicating some kind of state of that community nearby of that end, this informational crisis. Some funny stories started, which led me to realization of necessity to speak about this as openly as possible. Some younger people, extremely good mathematicians, believing in classical results, started to prove, give new elementary proofs of all well-known results using unproved theorems. That's not analyzing them, maybe they making some logical search, maybe elementary looking theorem contains deeply inside what they are going to prove as it happens. And not saying that it was never written. So this is state of topology, how I came to necessity to speak about this informational mass openly. And so these things is certainly not just, say, some, not obliged personally to some, say, big point of some outstanding scientist or outstanding scientists. But it is just indication of state of society of that period. It was simply impossible in a society of 1560s. It would be immediately checked and openly said everywhere. It's completely impossible. It would be done. It's a good example of that kind was recently demonstrated by a community of people who were around Fermat problem with checking of what of Andrew White. So this was the kind how it should be done properly. So no informational mess at all should be admitted. And these discussions for that are very important. So after some period, indeed, it is very interesting, some kind of recovery of topology started. I think it started in the beginning from early 80s. And it was obliged to the activity of people who came from quantum field theory. First of them, like for example Sasha Polyakov, whose famous work in string theory implicated some fantastic breakthrough in classical problems going back to Poincaré, for example, but they themselves did not told any moment that they are doing topology. It was just some byproduct of physics. They did physics. They never told that they do topology. But later, people, very soon, almost same generation, beginning starting from Witten, they started just to abstract topology openly using quantum field theoretical methods and reached, always the community reached fantastic success in that. Found, say, new dimensions, sometimes coming back to classical problems of topology of 50s and 60s, from completely different point of view. Sometimes unified forces, like in three-dimensional topology, were formed with activity of topologists of our time. Activity of symplectic topology also was important in that recovery, but it was also partly arranged by the theoretical people. But what is important is following. Well, how many mathematicians actually learned quantum field theory? I mean people with mathematics education, trained originally in mathematics. My old friend Zinger did this. Well, he's 75 years old now. Then he spent tens of years doing that, learning that. When I heard his talk 10 years ago, about 1991, in Milner's conference in Stony Brook, he made his first beautiful work, applying quantum field in topology, and how he started his talk after 10 years of learning. Everybody knows he started after 10 years of learning. He was another interesting person, that's Maxim Kontsevich, 40 years younger, also reached, learned this. It's also, I'm saying only about people who are proving mathematical theorems in topology. I don't speak about people who learn physics to do physics, for example. But even if you will add this kind of people, this list will be a bit larger, but not very much. Not very much. That's I'm saying now only about people who learn this for doing topology. So it's interesting looking, for example, in Ganzeli's work. It's interesting about quantization. Very nice to see how beautiful intuition which came from Feynman diagram for very simple topological quantum field, zero-dimensional quantum field theory leads, when you show it finally to mathematicians who does not know it, to some kind of magical, beautiful results. It is interesting that very important connection has been found in framework of string theory with integrable solitary systems. It was a remarkable discovery made by a group of theoretical physicists for physics. It was David Gross and Sasha Migdal participated, Prezan, Pezakov, Douglas, and Schenker. Pity that no one of them is here. Found out in connection with matrix models, string theory, remarkable connection of this quantum theory and integrable soliton theory, with E-type and so on. Very soon, Ed Witten pointed out that these ideas can be applied also to topology by some modification of model topological for calculation of Chern numbers of model spaces, model spaces with number of fixed points, with natural line bundles. Just some natural generating function of them, according to Witten conjectures, can be expressed through as solution of KD hierarchy, simple solution, rational, but just series whose coefficients may be easily calculated, therefore, as a correlate from soliton theory. And well, extremely beautiful set of ideas has been presented by Maxim Kontsevich for solving it. He even was capable to transform original quantum field theoretical model for doing that, so-called invented famous matrix A function and constructed diagram decomposition, which is topological for that. It is interesting. However, there is some interesting point here. If you cannot just simply define Chern numbers of model spaces, of Riemann surfaces with punctures or not. You have to complexify it somehow. And this beautiful approach, combinatorial approach from quantum field theory led to some natural compactification, natural from this point of view. And let us call it Stöber, Penner, Kontsevich compactification. It was published in Russian journals, Functional Analysis in 1991, where papers were checked properly. And so, well, but 1 year later, very good, remarkable work, I would say. I admire it very much. But 1 year later, it was claimed that this compactification is exactly coincide with standard compactification of the Riemann-Mumford. By the way, until now, I don't know whether, I'm pretty much aware that no proof appeared during last 7 years. Maybe Maxim will just tell us whether it is going to be proved or not. Well, it is not proved in the literature. In the literature, it's not. Yeah. Let's be careful with many experts. Okay. So, well, so my basic question is good to clarify some things. If there is some even controversial opinion, just put some nice subject for discussion. It is, and certainly, but certainly we have to ask the following thing: will mathematician learn quantum physics at all? It is a very difficult problem. It's not easy to learn it. I told about some best mathematicians who did it, and as I told you, if you look at people who learned it for doing, say, not only topology but physics and so on, there will be, say, 3-4 names more. Some of them are here. But so, and this is important in my opinion. It's very important in my opinion to do that. I am pretty much aware that, for example, if, say, higher authorities will grant us any confirmation of supersymmetry in real elementary particles, all quantum field people who are doing topology now will be away within 1 day. Just temporary home for them only in topology. That's, so it is very important, and I believe that many years I am trying to make propaganda of that necessity, but so things are developing very slowly. So let me now just stop this discussion. That's of course, it would be very interesting to clarify the subjects which came into these considerations. It is extremely important, in my opinion, for young people to know properly whether problems are solved or not, because young people don't want to prove other people's theories. They want to solve problems with the credit.
All people also want.
Very brave people I met in my life who were capable to acknowledge themselves at some level. That's very good number. There are such kind of things in dynamical systems. Let me point out that also as an end of my discussion, which is not my area, but I checked with many experts as well, that so-called classification of finite group does not exist as a fully proved mathematical theory. So informational math is not only what only topologists are. So let me go now to main body of my talk and to speak you now about topological phenomena in the single crystal normal metals. So let me avoid any introduction in quantum theory, just come to my real business. What is metal? A single crystal metal, you think that there is a lattice in nature of physical space, or d-dimensional space. D equal 1 to 3 are important physically. And of course, this quantum crystal itself is quantum object. It's naive idea about crystal, that it is just naive lattice space. It was found many years ago in classical physics, but classical physics will generate ordinary current, which is, or magnetism, ordinary current, say 1,000 times less than it is in reality. So for elementary normal metals and conductivity theory is essentially quantum. From the beginning, it was discovery of great physicists in Germany, Bloch in the early 50s, just a early period of quantum mechanics. Ordinary metal or single crystal is quantum object from the beginning. You don't need for quantum mechanics any kind of superconductivity and so on. It is always so. It is quantum object. It is Dutch, completely coherent system. But ordered. It's not control systems which are needed for, say, something. Completely ordered Dutch quantum system. There is a dual, if you have lattice, which is discrete subgroup, free variable subgroup in space. The dual is reciprocal lattice, which is naturally defined in dual space. Naturally defined in dual space. And in dual space. And factor space is a space of quasi-momenta. It is dual space. It's definition of space of quasi-momenta. According to elementary quantum solid state theory, the states of electron in the metal or in single crystal is completely defined as a point of this torus, quasi-momentum torus, and positive integer number n. There is a function, so-called dispersion relation. You may deduce this picture from the one particle approximation and Fermi statistics. which works surprisingly. So let me drop any introduction in quantum theory and tell you following thing. I would like to speak about some topology and geometry in the space of quasi-momenta. I started to do this in late 70s when I cleaned a fog from physical fog from what my friends in Landau Institute told me. For example, in 1980, I studied, for example, two-dimensional case, and my ideology was the generic Schrödinger operator, that you should not assign any topology to the whole family of Schrödinger operators with, say, analytical coefficients, that you have to specify only generic transversal one following the standard ideology of differential topology. And in that case, for example, if you have rational magnetic flux, so you may see that Schrödinger operators in Euclidean space in L2 is equivalent to the family of Hermitian operators with discrete spectrum, or say Hermitian matrices, like operators with discrete finite spectrum, depending on the point of torus of quasi-momentum as from parameters. So number of parameters is always equal to the dimension of space. It is important. And so, in particular, co-dimension of the subset where eigenvalues are equal to each other, so you have multiplicity is equal to 3. In two-dimensional case, you will have generically families when all individual eigenvalues will generate line bundles over the torus of quasi-momentum. And each shared number leads naturally its first quantity, which I studied a lot in 1980. This kind of quantity can be defined well for rational magnetic flux only. So you have series of dispersion relations and series of shared numbers. It's interesting to study where asymptotics for large n. Really, it is only local topological set of invariants. They are locally stable under small variations. Locally stable under small variations. If you would like to have just global topological invariant, you have to consider some kind of sum of them, or only after that you can extend this to rational fields, as it was done, I believe, by Alan Korn. But individually, these dispersion relations and shared numbers can be defined only in that setting. Now let me just start main body of my talk today concerning works which have been done recently, and I did it in collaboration with my student. He is physicist. It was published recently in physics journals, including a survey article, and it concerns three-dimensional case, three-dimensional normal methods. Let me tell you that it is not full list of references, proper references, because later I will show you that these physical results are based on all activity of people from my seminar which started from 1982, and so I will give you names of people who made important topological breakthrough which finally led to physical results. So that's not physical results were obtained only recently. It took years to understand simple things, how it is related to real physics. So let me tell you following. So you have just a torus of three-dimensional quasi-momentum. Torus is just generated by reciprocal lattice in dual space. And there is a selected surface for metals obliged to Fermi statistics of electrons, so-called Fermi surface, which is two-dimensional surface in periodic three-dimensional surface in R3. But you have to keep in mind, you have to pay attention to following thing, that all this stuff is in fact invariant under action of reciprocal lattice. So therefore, in fact, it is compact surface in the torus. It is compact two-dimensional manifold, closed surface without boundary in three torus, quasi-momentum. quasi-momentum is space of quantum origin, but we are doing normal geometry and topology in it. Well, first of all, let me point out that quantum physics does not know any natural restrictions, analytical restrictions, which kind of Fermi surfaces it might appear. So in principle, you may say that it might appear anywhere. For example, for the natural metals, which from Mendeleev table, if you are doing something like lower positions in Mendeleev table, like lithium or something like that, you will get something like sphere, trivial topology here. But if you are dealing with, but you should not think that it is always so. For noble metals, it is not so. It was first discovered by Pippert in 1956 that genus 3 might appear for copper. It is still simple. Not because of genus, but its geometry is very simple. But for such a metal like single crystal gold, it is genus 4, complicated surface. And some of my friends whom I started to make contact in Washington, now working in the Applied Laboratory, told me that, if you are saying that gold is complicated, no, it is very simple. We shall show you very complicated, real complicated Fermi surfaces, but they are doing new materials now, a lot. So to have complicated genus, you may, for example, gold is a very good example for demonstration, but you may need a lot of more complicated things. It is not which kind of topology, it appears, of course, geometrical pictures appears in that kind. You have to consider them in one brilliant zone, in one lattice, but like that. This is, say, trivial case, genus 1 case. This is rank 2, topological rank 2, and topological rank 3. Topological rank of Fermi surface is rank of image of fundamental group of surface in fundamental group of torus in 3 lattices. So rank 3 is more complicated. Most complicated situation, which is interesting for us. Of course, after making identification of equivalent boundaries, you will see what I told you. But in gold, for example, you have more complicated picture. You have also handles going along diagonals and so on. So you will have more genus performance for gold. But it is not topology which I am talking about. That Fermi surfaces are known, but only its most topological phenomena in physics appears when you add magnetic field or some kind of generalizations like Mills field and so on. In the weak magnetic field P, electrons move along the plane sections at Fermi surface. So you have Fermi surface. Consider it as a just universal covering to the space. It could be just periodic surface, periodic system of cubes, something like that in free space. You have family of plane sections orthogonal to magnetic fields, and this is electron trajectories. Geometrically, this system is trivial. But still you have to remember that you have to factorize all picture by the lattice. It is not obvious that it is trivial dynamical system. I told that magnetic field is weak. Why? It means that my magnetic field should be big enough such that it does not reach quantum breakthrough limit. Weak in that sense. But in real metals, three-dimensional metals, quantum units are measured in units of magnetic flux. And the magnetic flux is integral of magnetic field along the elementary lattice. But elementary itself of lattice is so small in real terms, 10 over -8 centimeter 1 angstrom, such that we need huge magnetic field to reach 1 quantum unit of magnetic flux. So all strong magnetic field until now are weak in theoretical sense. So it's okay, we may say, so we may use semi-classical picture, semi-classical in non-standard sense, in sense that it is not semi-classical in the classical sense, like people discuss. It is just some kind of stupid terminology which appeared in physics community. Better to say that it is adiabatic approximation instead of real eigenfunctions. But people say what? They extract quantum picture for electrons, but add magnetic field as some classical quantity after that on the form of quantum picture. This is like a mixed picture. There was a great solid-state physicist in Soviet Union, in in fact, Lifshitz, many years ago. He created extremely good school. Some of his famous former students like Asbel are working here in Tel Aviv University now. And this school formulated fundamental principle that for large magnetic field, the leading terms in all essential phenomena should depend only on geometric equation. That's of course every time in confirmation. Just about what means large magnetic, weak magnetic field? Weak magnetic field means more or less, say, you may go almost until 1,000 Tesla quantum unit. But say 20, 40 Tesla will be just available now as a very strong magnetic field. And let me remind you that 1 Tesla is about 10⁴ Gauss. So all this stuff is from the point of view of PDEs non-linear. That I don't know from which point to start, but so we came to topological picture non-linearly, and after that there will be one more step, non-linear relationship between topological picture and final physically observable quantities. So anyway, even if you did some piece of work which we did, say, in good rigorous topological sense, but still doesn't mean that everything here is rigorous. Rigorous foundation of physics is impossible. You will make, if you will create rigorous model, more rigorous model, you go more far from reality. So, from point of view of natural science, it will not become more rigorous than before. Normally. That's what's the extremely beautiful results that are obtained in rigorous mathematical physics, but it is not my aim. Let me pose topological problems in following form of elementary theory of functions. Consider plane, just plane, and quasi-periodic function in it with some number of quasi-periods. What can you say about topology of levels or connectivity components? That's, there are case k equal to 3, it's only elementary looking situation. Case equal to 3, you are dealing with three-dimensional terms. And it is exactly what I told you about electrons in magnetic field and lattice. That's if you will consider all family of these parallel planes. K equal to 4, interesting case, might be used in quasi-crystals, which I've investigated recently. So this is one form of problem. But you may say also that you are dealing with Hamiltonian system, as I told before. The Hamiltonian function is one value here. The Hamiltonian system, for saying which Hamiltonian systems are you considering now, you have to say which Poisson bracket are you considering. Poisson bracket should be constant with rank 2. In k-dimensional torus. In 3-dimensional torus, it is exactly magnetic field. 2-dimensional 2 by 2 skew-symmetric tensor of magnetic field always has rank 2 in 3 dimension. In 4-dimensional case, it always already will be some restriction. But really physical case is k equal 3, which I am discussing now. It is just magnetic field. Indeed, multidimensional visualization of the system of that kind, which, for example, has in mind people while writing beautiful work of Zolich and Tanzevich, this will be not that multidimensional visualization of that. They will consider something like surface line in multidimensional torus and family of hyperplane sections, which kind of. But our generalization, multidimensional generalization, is Is this system completely integrable, generically, or chaotic? And how to study its topology? I will demonstrate you that it is in fact more topology than ergodic theory. That in generic case here, generic in our class, in all physical situations as I described, it will be in a sense completely integral. It leads to regular topology, not to chaotic ergodic behavior. It is very interesting situation because if you will consider, it is equivalent to, in case of K equals 3 physical situation, you have Fermi surface, electrons moving along Fermi surface. It is a keep in mind this picture. And this is partial case of Hamiltonian systems on the surface. Making some natural change of Hamiltonian and annihilator, I may consider it as a Hamiltonian system on the surface with multivariate Hamiltonian function. And this system, this theory, has been considered in the literature.
A question. So you are thinking about what? You are speaking about a classical particle which the special relation is defined by the Fermi surface, and it's not quadratic, it's just
periodic.
Periodic, some sophisticated function, and
should be extracted from experiment.
Yes, put in a magnetic field. So
in magnetic field.
It's a system with three.
It is of course totally quantum object in fact originally, but if from point of view of dynamical system you are coming to that.
It's a 3 degrees of freedom.
Yes. Yes, of course, but you have to keep in mind that magnetic field is constant, and in one moment it reduces to the system on the 3 torus only in the space of quasi-momenta, and I just said about that. So I am dealing with space of quasi-momenta in constant magnetic field. Yes, this is, it is partial, as I told, but beautiful topological theory reduces to some topological models has been created by different people, Mazurevich, others. It's suggested by Riemann surfaces in this general system. Some new beautiful results were very recently obtained by Zorich and Kontsevich for generic Hamiltonian systems on the surfaces. But it is not our case, because in this situation of Fermi surfaces, it is non-generic from their point of view. And so all our picture is inside of measure 0. It is not, they don't see this, it is just they neglect all behavior which we have for all Fermis, for all our systems. It is a very typical situation as also between abstract dynamical systems and natural sciences. They invent some notion of generic properties in some class abstractly defined systems, but how to check whether they will be so generic in real nature or non-generic. In this case, for example, we have answer that our system, physical system, is in a sense is case which cannot be treated by that generic theory. It is strictly non-generic with completely different behavior. So let me define two types of trajectories. There is a trivial type of trajectories, compact trajectories. Compact trajectories on the torus, it is not only periodic trajectories, but periodic trajectories homotopic to 0. They remain periodic on universal covering. And quasi-periodic trajectories, they should lie in some strip along the straight line in the plane. This I call periodic and quasi-periodic trajectories. By the way, you may see that not only topology of Fermi surface is essential, but also geometry. Let's look in such picture. It looks like more complicated than ordinary cylinder, yes? But every plane sections here will be compact. So it is much simpler from point of view of dynamical systems than more trivial surface. Quasi-periodic trajectories can be visible in such type of pictures. Like here, on the universal covering, which is, I believe first examples were found by Ilya Lifshitz and Pishansky many years ago of some specific example of quasi-periodic trajectory when Cooper appeared. And indeed, they started to do some non-trivial investigation about 1960, but you have to take into account that it was at least 20 years ahead of time, and the community of physicists, they didn't know anything about nonlinear dynamical systems, that no one was able to understand it. They found some beautiful examples, made some mistakes, and development stopped. These mistakes were corrected only by, in our work, these people accepted that, it's not a question. Huh? But it was not time. Physics community started to learn dynamical systems, I believe, from mid-70s only. It was many years ahead of time. This is references. First time I just started to discuss that, I borrowed it from physics community and realized that it is non-generic, started to make some conjecture in 1982. And first important breakthrough in simple but beautiful work was done by my undergraduate student Anton Zoric. I returned to this subject several times, reconsidering conjectures, what should be done. Very important breakthrough has been, topological breakthrough has been done by Dinikov. But even when I made subject in this, talk in this subject in Misha Gromov's 50 years conference, anniversary conference several years ago, there was no idea that it is possible to apply finding observable phenomena. So it was found later. So you may find recent survey of our article in physics literature and Dinikov in mathematics literature about pure topology of that stuff. Recently I made also some multidimensional generalization. The statement is that our system is generically, systems are generically completely integrable for the most direction of a magnetic field in the sphere for every type of Fermi surface. It is general use statement. And how to describe universal asymptotics of conductivity tensor, electric conductivity tensor in the normal metals. Generic, now I told you that if I will consider all, for example, all family of Hamiltonian systems on the surfaces, Riemann surfaces, for example, real parts of holomorphic forms, yes? It will be, generic behavior will be Erquedist. But if I will consider this family of this, you have arbitrarily surface homologous to 0 in the free torus, and family of its plane sections on the universal coverage, yes? This is, we may, generic in this family, generic direction of magnetic field, and generic surface. Generic in our class, within our class. Yes, within this class, but not within all family of Hamiltonian systems on the surfaces suggested by algebraic theory of Riemann surfaces. Yes, it will be generic in our class, instead of these physical problems. For example, fix some good surface in the torus, so it will be generic magnetic fields, generic direction on the sphere. It means that what I am saying is going to be valid for the open set of measure 4 pi on the two sphere for magnetic field. Not torus, but there is also there is a Fermi surface in it. Yes, yes, it's very simple geometry. Of course, it's a restriction of constant form, you may say. It is same as plane section on universal coverage. It is no question about that. And this is highly non-trivial system. The examples has been constructed by my people from my seminar, Tsarev, but that's some well-known guy from function theory, Kanyagin, helped him to find when you might have chaotic behavior for some set. It is not so that it is always completely integrable. It might be chaotic behavior sometimes, but generically it is completely integrable. I will explain you a little bit non-standard notion. In particular, all trajectories are quasi-periodic. I defined before notion of quasi-periodic trajectory. But let me formulate first just physical corollaries from that, observable physical corollaries from that before formulating topological theorems. And first of all, which kind of consider conductivity tensor in the given magnetic field for the electric current. So you apply electric, what is conductivity? You apply weak electric field and you look on the current. There is a linear operator connecting these two quantities. They call it conductivity tensor. It is free by free tensor. I am looking on the behavior of conductivity tensor in the plane orthogonal to magnetic field. There is a trivial topological type. Trivial type. Before Lifshitz, there existed conjecture of famous experimentalists like Kapitsa that it will be always so, but Lifshitz disproved that in his famous works, that for large magnetic field, this conductivity tensor will just decay. Like inverse power of magnetic field, some components like B minus 1, some components B minus 2, like that. But there is a second situation is possible, that limit of electric conductivity tensor in the given magnetic field is given with fixed direction, may be non-trivial, plus some remainders. And its eigenvalues should be such that one eigenvalue should be still equal to 0, but second one non-zero. That is important property, that one eigenvalue still should remain to 0. This result is already new. It contradicted to some specific calculations which Lifshitz group made, that they accepted that there was mistake in their work. But it is not what is most interesting here. So it is some kind of tensor in the plane orthogonal to magnetic field plus some remainder, which is small. So there is always 0 vector of this, depending on magnetic field. All other cases corresponds to magnetic fields occupying set of measure 0 on the two sphere. Let me give you following picture. This is magnetic field, and this is, and E1 is a vector, which is, by definition, a vector of this 0 direction of conductivity tensor if the type is non-trivial. We may fix it. But this is topologically stable situation according to our considerations. And if you will rotate slightly magnetic field, picture will remain the same. And you will do that. You may realize this in principle, everything like that experimentally. You may do that. And you may do second experiment, and you will find two such. New magnetic field, new 0 direction. So you got already 2 vectors. You may do this infinite number of times. You may do this infinite number of times. Our statement is following, that no matter how many small rotations of original magnetic field are you going to make, if you will, all these 0 vectors of conductivity will lie in one plane. So you have 2-dimensional spot of magnetic fields, but it is 1-dimensional plane of directions. And this plane is going to be integral. It means that what is integral plane in free space? It is a plane generated by 2 reciprocal lattice vectors. It is, so you can extract free number of free integers from that situation. This is topological type of this zone, of this stability zone. This type of invariants, they are, in a sense, reminds you analogs of integral quantum Hall phenomena. They are not belong to global topology. They are subject of local topology. They are stable only under small variations of parameters. If you will rotate magnetic field more stronger, so everything will disappear, or you will come to trivial topological type, or you come to some different topological type. So topological types where are numerated by 3 relatively prime integers, and they depend on magnetic field, and given Fermi surface is given. The sum of them is a set of full measure. For copper, only trivial topological type appears, so nobody pays attention. We reconsidered all experiments made, say, 35 years ago in best institutions, and found that for gold, it was visible this type of topological type. Of course, nobody asked that questions, but you may see that from that pictures. And huge number of smaller spots has been found at that time, which may be suggested that much smaller size of topological zones of smaller size appear as well, or even might be stochastic. Let me tell you following thing. More complicated topological type were maybe expected in some dots. But you see, if you will consider subject mathematically, let us consider following example. Consider this very simple Fermi surface. Sum of three cosines, first variable say x, y, and z. Just I am writing variables of quasi-momenta with dimensional parameters, but it is first variable, second variable, third variable. Some of them is 0. Very simple Fermi surface. It is indeed very complicated object. Infinite number of topological types appears here numerically. And certainly it can be proved analytically that even stochastic behavior will appear here in some fractal set of smaller, some fractal codimension. 5. This is cubical lattice. Huge symmetry appears of that. There is some interesting conjecture about how many ergodic regimes you may have. In principle, this is a very specific case when you have even function reflected under epsilon minus epsilon levels are equivalent. And in this case, everything is concentrated. All difficulties is concentrated in 1,0 level only. A small perturbation of this level, epsilon, will lead only to finite number of topological types, increasing for smaller epsilon. It is for such even functions. It is normally this phenomena will be distributed between all levels of Fermi dispersion relations, but for this type of functions, they are concentrated in one level only. It is a specific case which should not be ignored. Its numerical experiment led to topological types like, say, 9, 7, 12, or something like that, few points on the computer, which has been done by my student Roberta De Leo in Maryland recently. Let me formulate this, my final theorems in topological terminology. First of all, in functional terminology, second one in topological terminology. It is following. Consider quasi-periodic functions in real plane. All levels, or connected components of levels, function equal to constant, are either compact or quasi-periodic along some direction eta in the plane. This direction is stable under the small variation of parameters, all parameters, in the following sense. After variations, all directions eta lie in the some integrable hyperplane, which is generated by lattice. And this is, in fact, two-dimensional homology class of the torus. Two-dimensional in three-dimensional case and three-dimensional in four-dimensional case, where it's proved only for this two dimension. And in dimension 4, it is proved not for measure 1, but only for open set, dense open set on this sphere. Function, quasi-periodic function. It is quasi-periodic function. It is periodic function in k-dimensional. Okay. Yes. It only looks like theory of function. In fact, it's highly non-trivial. Three-dimensional topology appears in that situation. Huh? Yes, in the plane orthogonal to magnetic field, the quasi-momentum, it's not momentum. All this topology of normal of metals obliged to the lattice, that it is not momentum, it is quasi-momentum. Torus is compact manifold, it is important. Yes? That's, yes. Excuse me? Which rotation? It is motion along complicated with naive opinions. Don't work when you have complicated anisotropic dispersion relation, rotations and so. It's Maltsev pointed out that for stochastic trajectories, which even conductivity along the direction of magnetic field might be blocked. That's a naive idea that its rotation in plane orthogonal to magnetic field fails here, because obliging to topology of Fermi surface and direction of magnetic field, they are moving, might move along open trajectory. No, it's the same. If you found rotation of quasi-momentum, you will find after one quadrature rotation of particle, yes. It is highly anisotropic behavior in the space of quasi-momenta. And in such, like, if you will look on Fermi surface for gold, you will find out that such naive ideas from standard Larmor orbits will not work here, yes, that's at all. All this picture is obliged to this huge anisotropy and topology. So let me give you another form of more topological formulation. Consider Fermi surface of some dimension in the torus, and it is surface homologous to 0. And consider family of plane sections, always plane sections. I have two cases only, k equal to 3, physical, and k equal 4, which I found some generalization very recently, and might be this will work for quasi-crystals. It's not physical applications, not done yet for k equal 4. For k equal 3, what I was told about them today. Remove all compact sections from the Fermi surface. All compact non-singular sections remove. What remains will be some family of pieces of partial Fermi surfaces. Or it might happen that all trajectories are compact. So it will be empty, trivial topology will work, conductivity tensor decay with high magnetic field. But it might happen that remainder is non-empty. The pieces, we shall call pieces the carriers of open trajectories. It is topological carriers of open trajectories, not like closure in sense of ergodic theory, it's topological closure. And you may fill in these pieces by disks in corresponding planes in the natural way. And they became closed manifolds, set of closed manifolds. The theorem, which is in fact lies in heart of this all our consideration, it was not formulated in this form in original works, but it was extracted for needs of physics in process of doing applications, essentially from the proof which has been found in topological breakthrough of Zorich and Dinikov, but in this form it has been put in process of doing physical applications. That homology class of these surfaces is one, undivisible, unique up to sign plus minus. So you have several pieces here, or even number indeed. It cannot be one, at least two, because some of them should be homologous to 0. And it is same homology class, all of them given, unique up to sign, non-zero necessarily, lying in this group, in integral group homology. And these manifolds all are homeomorphic to torus. And this is in sense what I told, that it is some kind of very interesting kind of complete integrability in this case. It leads, it is with additional integer valued properties, I would say, that is torus. It is proved for k equal 3 for generic case. It might be non-true for k equal to 3 for some non-generic case. For k equal 4, I proved it recently for the open set in the in Grassmannian, which is everywhere dense only recently. That's, so this is which kind of, and in physical case, it means that all these handles, carriers of open trajectories generically are genus 1 only. There are examples that they are genus, higher genus, but they are non-generic. That's measure 0, occupying measure 0. This is just results which I wanted to tell. That's, this existence of such counterexamples makes proof very hard topologically. It is non-trivial problems of three-dimensional topology, but luckily that's everything here works well. There is interesting question, somehow maybe also concerning probability, what is going on with non-generic case when you have ergodic, chaotic type orbits. It is still possible to observe them. Today's precision is very high for observation in solid state physics. There is idea of some scaling behavior here. I don't know whether there is any analog of Feigenbaum universality in this case. It is essentially much more complicated situation than just simply more maps of interval. But you may expect that generically generically with conditional generically with having chaotic orbits, you will have some kind of scaling, and interesting physical phenomena will happen. Even conductivity along the magnetic field might be blocked also. Okay, thank you very much for your attention. Of the system is just Fermi functions. I told you there was such case. In presence of without magnetic field, the points are staying. This is point is just electron. Only in presence of magnetic field they start to move. And the Hamiltonian is Fermi function, and magnetic field is Poisson bracket in Platon after reduction to Platon. And annihilator is plane, so you have plane sections of Fermi surface. But doing consideration only in this surface, you may use duality, and you may forget about our part of torus and to replace this annihilator by saying that it will be multivariate. Traditional Hamiltonian is in 6th space. I made elementary reduction to 3-dimensional space using the magnetic field is constant. And in this case, I have Poisson bracket of momenta is exactly magnetic field. And so this property is valid also for quasi-momenta. Yes? So it is Poisson bracket, it's exactly magnetic